Do you want to pass your classes? Then keep watching. This time we're going to be starting. This is going to be the first video of Chem 2C, the intro video. I'm currently making this video 2 weeks into the class as a way for a form of learning for me to come back to later on when I'm taking the midterms and the final in the future. And it's also a way of explaining to other people, and also if the opportunity is given, people who are currently taking the class right now as well. For this video, the first part of the video, we're going to be doing the first part. I'm going to be explaining the first part of the prerequisite of the class that you kind of have to understand other subjects of the class, which is redox reactions. Now, redox reactions are something that I believe that it is taught in Chem 2A or other prerequisite chem classes, but it's a prerequisite for this class specifically. So I'm just going to be going back and reviewing it because it was a kind of I remember learning about it in Chem 2B, and it was a little bit of a difficult concept if you didn't properly review it. So first, there are two parts of the redox reaction. It's the reduction and oxidation. So what is reduction? Reduction is when an element gains an electron. And the oxidation is when an element loses an electron. And how I remember this is, let me write it down to make it easier to remember. So let's use an element, zinc, for example. When zinc is reduced, so this is the base form of zinc, it's just zinc with no charges. But then when zinc is reduced, it becomes zinc, say, loses 2 electrons. It gains 2 electrons. It becomes 2 minus. And the reason why it goes from having a charge of 0 to having a charge of -2 is because electrons are negative. So when zinc gains electrons, it makes the whole element have a negative charge right here. So it will mean that this zinc gained 2 electrons. And how I remember which is reduction, since oxidation is opposite, how I remember is reduction means the charge is reduced. That's how I just personally remember it in my head. There are other acronyms and ways to remember it. And oxidation, let's use the same element, zinc. Zinc being oxidized would become zinc 2+, which means it is losing an electron. So let's say electron has a charge of 1. If you do 0, which is the charge it has now, minus -1, you know how minus changes it to plus. That increases the charge plus here. So for reduction, it's reducing the charge, which means it's gaining an electron. And for oxidation, it's gaining the charge, which means it's losing the part that makes negative the electron. Now, how do we determine the charges of certain elements? So generally speaking, certain elements, they have charges that are already known. So something like, if you've done chemistry before in the past, if you have a history of chemistry, you should know things like ammonia, which is H3. It doesn't have a charge, but when you add an extra H, H4, it becomes positively charged. So now you know this ammonia is positively charged. And something else like sodium chloride, which is basic salt, you should know that the Na is usually positively charged and the chloride is usually negatively charged. And these are going to be the same for redox reactions. You know the chloride is always going to be negative and the sodium is always going to be positive. But you don't have to particularly remember these, as there are ways of determining specific elements, the reduction, or they call it oxidation states, to know the charge it has. Oxidation states. And there are certain rules to determine the oxidation states of most elements, most compounds in general. So the first rule of the series of rules, the first one to remember is elements in their natural states usually have an oxidation state of 0. So elements like these would always have a oxidation state of 0. And then another rule of the following set of series of rules is that the first one, oxygen, would always have a oxidation state of -2. I mean, not always, but it usually would have an oxidation state of -2, unless for compounds like OF2 and BO2. And you don't have to memorize these, as later on, especially this one specifically, I explained. It's concept based about why the oxidation state change, but generally oxygen usually has an oxidation state of -2, which is easy. It's what you should memorize and not that hard to memorize. And then hydrogen is usually +1. I think for this one, not just hydrogen, but all the alkali metals, so all the metals that are group 1 in the periodic table. So this group on the periodic table called the alkali metals. By the way, this is the periodic table from Google. I just put it on here. The alkali metals, these are usually a +1, like I mentioned earlier, in sodium chloride. Since sodium is an alkali metal, you know it's usually going to be +1. And the same goes for all these. And then another rule here is that elements like fluorine and other halogens are usually -1. So the opposite of these. And these are usually -1, like in chloride, -1. And those are the standard rules that would help you determine other compounds. Like if you see a compound, I'll show you examples, but if you see a compound that has one of these, you know that if it has oxygen, the oxygen is probably -2. If it has a hydrogen or any of these like lithium, sodium, it's probably a +1. And if it has fluorine, chlorine, and things like that, it's probably a -1. And then you use it to determine what the other elements in the compound is. These are practice problems that I'm going to be doing along to further explain these rules and how they work. So this compound, it has 2 elements in it, right here, iron and oxygen. And it's 3 oxygens, not just 1 iron. So I'll write it out here and call iron times 3 oxygens, which according to the rules we mentioned earlier, oxygen is going to be usually a -2. And then the total charge, you see how there's not a negative above here, or positive, or any charge? It means that the total charge of this compound is just a 0. So now we're trying to find the question mark. So we do 3 times -2, it's the question mark, times -6 equals to 0. And then we move 6 to the other side. And then the question mark is equal to 6. And since it's not F2, it's just 1 iron, that means Fe has to equal 6 if we follow the rules that O is usually -2. Now for the second one, the O, once again, we're using O again, which we know is usually -2, so we do the same thing. We don't know S, the oxidation state of S. And notice how this time it's 2 S's in the compound. So it's 2 times the question mark times 3 again times -2. And also the total balance of charge here is -2 instead of 0 is this one, so it's equal to -2. And then we multiply it out. 3 times 2 is -6 times 2 question mark equals to -2. Then we move 6 to the other side again. And then it becomes 2 times the question mark is equal to 6 minus 2 is 4. Then now we have 2 question marks is equal to 4. What must the question mark be? 5 by 2 question mark is equal to 2. So that means one of the S's is equal to, it has a +2 charge. Now for this one, this is one of the tough ones where oxygen is an exception. It's not -2 like I mentioned above. And the reason why is because fluorine here on the periodic table is more electronegative, which is something that I think you learned in previous classes as well. But what that basically means is that it wants to sense both. This usually would be -2, and this usually would be -1, and then there's 2. So it'll be -2 here. and it has to add to a 0 charge because the compound has a charge of 0. But it doesn't make sense because -2 minus 2 is -4, not 0. So what would happen is that the oxygen has to give way, since the fluorine is a more electronegative element, and it's the whole concept of charges is that fluorine would want to pull the electron away and attract it towards itself, which is why it has a negative charge. Usually has a negative charge. So since it's more electronegative than oxygen, which means it would want to pull the electron more to itself, fluorine would not be the one to give way, since it has the power to be more negative than oxygen. So the oxygen has to give way for the charge to equal to 0. So the oxygen over here has to be 2 minus 2 for it to be 0. And that's why the oxygen charge here is 2. And then the fluorine charge here remains -1, but they're two fluorines, which is why it's 2 minus 2 is equal to 0. And then for this one as well, this is also an exception here. So usually would want this to be -2 times 2, -4, plus K is a alkali metal, and it's usually a +1 charge, and then it's times 2. So it should be a 2 minus 4 equals to -2, but the compound over here doesn't have any charges to it. It should be equal to 0. But over here we see it's equal to 2. And to change that, we can either make K have a charge of 2, and it will be 2 times 2, 4 minus 4, to make it right 0, or we can make oxygen have a charge of -1 instead. So this would remain 2 minus 2, which is 0. And for this problem, we picked this one, and the reason why is because K is an alkaline metal, and if you remember the anatomy of a metal, an atom is K, potassium only has a valence electron it only has one valence electron. So for it to have a -2 charge, for it to have a 1, so for a negative charge, it has to lose electrons, remember? So it can't possibly have a charge of 2, which makes it lose 2 electrons. So it would have to go with the oxygen being the one to give way and have a charge of -1. So this can hold true. Okay, now we figured out how to know which element in the compound is being reduced and which is being oxidized. Remember, reduced is the charge when the charge is negative, it went down. Oxidized is the charge went up from the previous charge. We can use that knowledge to do something called, that's the main point, the redox reactions. And for these, we're going to start off, instead of doing full redox reactions, we're going to start off doing half reactions. But I'm going to give the rules for doing redox reactions. Right here, these are the steps for doing a redox reaction. So for redox reactions, including half reactions, there are two ways. It could be acidic or it could be basic. Acidic means that you can leave the final answer with H pluses in it, because in acidic solutions you have H pluses, but in basic solutions you don't really have H pluses because H pluses is inherently acidic. So we usually have OH minuses instead in basic solutions, and that's why it's different. So it's for the first 3 steps, both of them are the same, but then for acidic you can stop at H plus, and then for basic you have to add OH minus to take out the H plus, and you'd rather have OH minus than H plus in the basic reaction. So right here I'm going to do these problems to explain it. So for these, we're taking NO3 minus and it turns into NO. So we break down the elements, the charges in the elements. So for this first compound, NO3 minus, if you remember from earlier, to find, we're looking for the charge of N right here. And we know that O is usually a -2. So it's going to be -2 times 3 question mark times 3 times -2 is equal to -1. So that's question mark times 6 is equal to -1. both sides by 6. And you get the question mark is equal to, for the first redox reaction, it tells us that it's an acidic solution. So we now have to follow only step 1 to 3. So we start by balancing all elements except oxygen and hydrogen. So right here we can see that one end, the end's already balanced. So we can skip the first part and go straight to balancing oxygen. So in this one, 3 minus 2 NO. You can see that there are 3 oxygens here and only 1 here. So to balance it, we have to add, sorry, I gotta leave room. We have to add 2 more oxygens to it. 2H, 2O, 2H. The H2O supplies 2 more oxygens, and now the oxygens are balanced. But now we have a problem because there are 4 H's here on this side that aren't here. So to fix that problem, we just add 4 H pluses. And now this half reaction is balanced. We can see now that all the elements are balanced. 1 N, both sides, 3 O's on both sides, 4 H's on both sides. But right here, you can see that the charge, since we added H pluses, it messes up the charge. And the charges also have to be balanced in redox reactions. That's the final thing. After you do all these, make sure at the end the charges are balanced. So right here we have a charge of, this one has a charge of -1, and this one has a charge of +1. But remember, there are 4 of it, so it's +4, and that becomes -3. I mean +3. And over here we have no charges on top of any of the elements. Water is neutral, and that's neutral too. So it just has a charge of 0. So right here, the charges are unbalanced because over here it's a +3, and over here is a 0. So how we fix that is we just add electrons, because electrons are negative if it's positive, and if this side was negative instead, we add the electrons on this side to make it more negative to match. Both of them have to have the same charge. So we just add 3 electrons to this side, and then it cancels out the +3 charge, and now they both have a charge of 0. For the next one, the basic one right here, we do the same thing here. ClO goes to Cl minus. The Cl is already balanced, and then we go into the oxygens. This one has a 1 oxygen, while this one has no oxygens. So I just add a 1 H2 plus. So now they both have 2 oxygens. Here it has 2 hydrogens that this side doesn't have. So I add the 2 H pluses. And since if it's an acidic solutions, we just skip straight to balancing the charges. But since it's basic, we have to get rid of the H pluses because we can't have H pluses in a basic solution. So what we do is we add 2 OH minuses to get rid of it. And remember, whatever we do to one side, we have to do to the other side. And since H plus and OH minus come together and make H2O, neutral H2O, positive and negative cancels, and then 2 H's and 1 O, and it's 2 of them. So it cancels out both and makes 2 H2O. So the equation now becomes ClO negative plus 2 H2O goes to Cl negative plus H2O plus 2 OH minus. And since there are H2Os on both sides, one of them has to get canceled out. So since this one's 2, this one's 1, it's 2 minus 1. So this one goes away, and this one of these goes away, and you're left with 1. And now it's ClO minus plus H2O gives you this. Now we do the charges at the end. This side has a charge of -1. This side has a charge of -1 plus 2 negative ones. -2, -1, -3. So we have to balance the left side to also give us -3. And we do that by adding 2 electrons, 2 negative electrons. That makes the charge -3 now, and they both match. Now we know how to do half reactions. We can move on to the full reactions, which are so hard because of the amount of mistakes, possible mistakes you can make in these. But if you do them right, if you follow the rules, then you can avoid the errors. For these, how to do full reactions, they're just like half reactions, like these we did up here, but instead we do it on one side, and then we add both reactions together. For half reactions here, we split them, for full reactions, we split them into two. So remember how there's reduction and oxidation? We figure out which is, we don't necessarily even have to figure out which is reduction or oxidation, but for the purpose of doing it right, I will. For this one, as you can see here, the Fe, the iron, has initially a charge of 2 plus, and then at the end it has a charge of 3 plus now. So the charge is going up, which means it is being oxidized. Right here, the oxidized element is the F2 plus, which means since it's being oxidized, it means it's the reducing agent. And now what is being reduced? It has to be the other thing, right? Because right here, Cr2O. Oh, this is a tough one. So Cr, it's 2 times the question mark plus 7 times negative 2 is equal to negative 2. 7 times negative 2 is negative 14. 2 times the question mark. Now we move 14 to the other side. Then it becomes 2 question mark equals to 14 minus 2 is 12 divided by 2. 2 question mark is equal to 6. So right here, the charge of chromium is 6, and now at the end we can see it's 3. So yeah, it is being reduced. Chromium is being reduced. So now we split the full reactions into half reactions, and we do them separately. I'll do oxidation first. So right here it's Fe2 plus becomes Fe3 plus. Luckily for this one, there are no oxygens or hydrogens, so we can just skip straight to balancing the charges. Also, the ions are balanced, only one of each of both sides. And we can easily balance the charges by, this is 2, this is 3. To make 3 become 2, we minus 1, so we add a negative electron, so it's just plus E. And now you can go into the reduction part, which is the harder part of this problem. So it's Cr2O72 minus becomes just Cr3 plus. So straight away, as you can see, this side has oxygen, the other side doesn't. So we have to add 7 H2Os for 7 oxygens, and now we have to add 14 H pluses to counter the 7 H2Os. And now, initially I messed this. This is a mistake. I messed the whole thing up because I didn't notice, like the rules said, this is why you should follow the rules. I didn't start with the chromium. The chromium over here is not balanced, so I can't do all that. So I have to balance the chromium before I try to balance the oxygen or the hydrogens. So right here, I added 2. Oh, actually, in the grand scheme of things, it doesn't change much, but it's always important because sometimes it could change everything. So right here, it's still the same thing because I still have to balance the 7 oxygens here, 7 waters, and then 14 H pluses here. And now, since now everything is balanced because the chromium is balanced, the H's are balanced, the O's are balanced. So now, since all these are balanced, we balance the charges. So this side has a charge of 14 of the H pluses minus the 2. It's a charge of 12. And this side has a charge of 3 pluses, but since it's multiplied by 2, remember, it's 6 plus. So now we have to make 12 6 plus, we have to add 6 electrons to this side for it to be balanced. So now we have the half reactions of both the oxidation and the reduction. Now we have to add them together, but we can't just add them all together because, as you can see, the electrons have to cancel out. While this one only has one electron in its equation, while this one has 6 electrons. So we have to manipulate the equation to be able to have both electrons, because they're on opposite sides. They can cancel each other out. So to do that, we find the greatest common factor, I think. Yeah. And by doing that, since this one's 1, it makes it easier. We just have to multiply this whole thing by 6. And then it becomes 6 electrons, which is then able to get canceled out. And we write the whole equation out right here. Remember, this whole equation got multiplied by 6. So it becomes 6 Fe2 plus, and then plus these reactions on this side, plus Cr2O72 minus plus 14H plus, and the products, we have the products now, 6 again, Fe3 plus 2 Cr3 plus 7H2O. Now finally, for the last one is, I think the last one's basic, although it is not stated in this. Now for that last problem, looking at this, although it's not stated, usually it will normally be stated, but I'm pretty sure this is acidic as well. Both of them are acidic, because this looks like bromic acid. It looks like the conjugate base of bromic acid. So for this, we do the same thing that we did earlier, where we split it into 2 half reactions instead. So right here, although this is an acidic reaction, and this is the final answer of the acidic reaction, for a basic reaction of, let's say this is basic, what we would do instead of stopping right here, is that we would add, before we get to this point, we would add 14 OHs to both sides, because we can't leave it in, we can't leave a H plus in a basic solution. And this would basically change to, instead of 14H plus, we would have, this would become 14 waters, which would cancel with 7 waters. Would completely take these 7 waters out, and would be left with 14 waters. So 7 cancel 7, we'll be left with 7 waters here, and 14 OHs here. That's if the solution was basic. And we're going to skip the last problem. This is the end of the redox reactions for the first chapter, chapter 9 of Chem 2C. And for myself watching this in the future, right before the exam, I hope I do well in it, and I hope that everyone else who watches this learns something from it and does well in all their classes and future endeavors.